Sir, good evening, sir. Dr. ISN Raju garu, Professor Ramanujacharya garu, Dr. K. Sitaram Babu garu.
నమస్కారం అండి. నమస్కారం సార్.
నమస్కారం అందరికీ.
ఎలా ఉన్నారు? మీ క్యాటరాక్ట్ ఆపరేషన్ చేయించుకున్నారు?
ఓకే సార్, పర్వాలేదు, రికవర్ అవుతున్నా. రెస్ట్ తీసుకుంటున్నా సార్ ఇంట్లో.
ఓకే.
సార్ సీతారాం బాబు సార్, స్టార్ట్ చేద్దామా సార్?
Just wait for 2 to 3 minutes, sir. Now 6:30, we will wait 6:30 to 6:30. Sir, we'll start, sir. We'll start in a couple of minutes.
Yes, sir. గుడ్ ఈవినింగ్ మొయినుద్దీన్ గారు.
హలో,
Good evening, sir.
గుడ్ ఈవినింగ్.
Good
గుడ్ ఈవినింగ్.
వెంకట సుబ్బయ్య గారు, ఏంది అందమైన అద్దాలు పెట్టారు? కంటి ఆపరేషన్ అయిందా?
అయింది సార్, తెలీదా? మొన్న మీటింగ్ కూడా రాలే కదా నేను.
అదే,
క్యాటరాక్ట్
ఏ కన్ను?
రైట్ ఐ.
రైట్ అయ్యా. ఓకే. బాగా కనిపిస్తున్నాయి సార్ అద్దాలు పెడితే మీరు.
థ్యాంక్ యూ. నాకైతే ఇబ్బందిగా ఉంది.
ఎందుకు బయటికి ట్రాన్స్పరెంట్ కనపడట్లేదా?
డల్ గా డిమ్ గా కనపడుతుంది.
కాలేజీకి వెళ్ళట్లే?
లేదు సార్, మెడికల్ లీవ్ లో ఉన్నా.
ఓకే. గుడ్ ఈవినింగ్ సార్, సీతారాం బాబు సాబ్.
గుడ్ ఈవినింగ్ సార్.
గుడ్ ఈవినింగ్ ఫర్ ఆల్ దోస్ ఆర్ జాయిన్డ్ 17th members. గుడ్ ఈవినింగ్ సార్, విష్ యూ హ్యాపీ బర్త్డే సార్, మన ఐఎస్ఎన్ రాజ్ సార్.
నమస్తే. నమస్తే అండి. నమస్తే.
సార్ విష్ హ్యాపీ బర్త్డే సార్, ఐఎస్ఎన్ రాజ్ సార్.
థ్యాంక్ యూ సో మచ్. హ్యాపీ బర్త్డే సార్.
ఇన్స్టిట్యూట్ లో ఉన్నారా సార్? ఇన్స్టిట్యూట్ లో ఉన్నట్టు.
సార్ సీతారాం బాబు సార్ స్టార్ట్ చేద్దాం సార్.
Okay, sir. Sir, good evening to one and all, sir. Today, we are going to have the National Science Day, a webinar. The topic basically is radon technology. It was delivered by engineer G.V. Ramapattarao garu, is NTC and RCI DRDO. I invite G. Venkateswara garu, chairman of the Telangana State Center, convener of the event, Professor Mohammed Mohiuddin garu, our council member, ISM and past chairman, and also some of the prominent figures who are part of the webinar. T.V. Rasan garu, Dr. Gandhi, Perumalapalli, L. Prabhakar Reddy, Murali Krishna, A.K. garu, Narendra Sri Ramoji garu, Pavitri, Pavani Shravya garu, Pratap Babu garu, Ramanjneya garu is one of the senior members of our Institution of Engineers, R. Gopal Krishna garu, Rajalakshmi Saifon, and Shankarai Swami garu, and Vanam Srinivas. And also invite some of the names that I have not read, which also include the FIs, life members, corporate members, and also research scholars being part of this National Science Day. With this, I request the chairman of the Telangana State Center of Institution of Engineers to present out the event.
Thank you, sir. Respected keynote speaker, Engineer G.V. Ramakoteswara Rao, Scientist G, RCI, DRDO, Dr. K. Sitaram Babu, FIE, Honorary Secretary, IA, Telangana State Center, Professor Dr. Mohammed Mohiuddin, FIE, Committee Member of Telangana State Center and Convener of today's event, Dr. ISN Razu, Council Member, IEI, Ayanki Murali Krishna garu, L. Prabhakar Reddy garu, G. Kondalarao garu, Narendra garu, then Controller of Examinations from OU, Professor Ramanujacharyalu garu, R. Gopal Krishna, Rajalakshmi garu, Shankarai garu, all the invitees, ladies and gentlemen, good evening to all of you. Today I feel it is a great privilege and honor to be amidst this august gathering and extend a warm and hearty welcome to the keynote speaker and all of you for this important webinar on National Science Day. Today, I am very happy to be associated with this memorable event. I wish to inform that the Institution of Engineers India, Telangana State Center is organizing National Science Day on 28th February every year. The National Science Day commemorates the invention of the Raman effect by the great Indian physicist Sir C.V. Raman on 28th February 1928. For his discovery, Sir C.V. Raman was awarded the Nobel Prize in Physics in the year 1930. The day is celebrated to mark the importance of contributions made by scientists towards the development of our nation and the world as a whole. It is used to create awareness about the role of science in society. Today, Telangana State Center arranged a webinar on account of National Science Day with the eminent experts. And the technical talk is Radon Technology by Engineer G.V. Ramakoteswara Rao, Scientist G, RCI, DRDO, Hyderabad. Since all of you are anxiously awaiting to hear the talk from our eminent speaker, I am limiting myself and hope that you will really enjoy the talk on this important National Science Day. On behalf of the Telangana State Center of IEI and on my own behalf, I once again extend a hearty welcome to our keynote speaker, Engineer G. Ramakoteswara Rao garu, and all of you for this event. Before I request Before this, I request Professor Dr. Mohammad Moinuddin, convener of the event, to introduce our keynote speaker, Engineer G.V. Ramakoteswarao garu. Sir Moinuddin garu.
Yeah. So, good evening, sir. Respected our chairman Venkat Subbaya garu and our secretary Sitaram Babu garu and all those participants today. Good evening for one and all. So, it is a great opportunity to me to today introduce our today's this Science Day keynote speaker, Mr. G.V. Ramakoteshwar Rao completed his BTech in 1996 from JNTU Hyderabad and MTech in 1988 from IIT Kharagpur in electronics and communication engineering. He joined RCI DRDO in 1998. His area of interest are design and development of seeker antennas and radomes for airborne applications. During his career, he designed and developed a medium, wide, and a narrow beam monoplus antennas and a ceramic and composite seekers radomes for various projects. He is a member of IEEE Antenna Propagation and a Sensor Society of India. His work published in more than 6 journals and 25 conferences and proceedings. His area of interest is electromagnetic field, RF and microwave antennas, and radomes and frequency selective surfaces for airborne applications. So this is a very brief introduction given by G.V. Ramakoteshwar Rao garu. It's a great opportunity to me, sir. So to introduce you for our today's Science Day program for those who are participating. So thank you so much, sir. You are giving a valuable this Science Day program, and over to our chairman Venkat Subbaya garu.
Thank you, sir, Professor Mohammad Moinuddin garu. Now I request our keynote speaker, Engineer G.V. Ramakoteswarao garu, to proceed with his talk. Sir, please, sir.
Yeah, please. Good evening, everybody. I am privileged to be and honored to be giving a webinar on this radome technology, which is my throughout my career, whatever I put onto that. And also I wish you all IEI patterns a happy National Science Day. With that, I will start my presentation on radome technology. Because actually the radome is nothing but a radar dome. It protects the radar. Earlier, olden days, during Second World War, the radars are invented. The radars are big as a building. Now, this radome, when it comes to the seeker is nothing but an onboard radar, which is an airborne vehicle, which becomes a miniaturized radome, miniaturized radar. So its size is very, very small. That is nothing but seeker is nothing but a radar only, but it is on board because of the payload constraints. It is a smaller in size. So radome is a protective device which protects the electronics of the seeker, which gone through from various technologies. That what I'm going to cover. Radome is an it protects the antennas and RF environment which is there inside without interfering the electromagnetic performance of the electronics, which is inside the radome, inside the missile, inside the airborne vehicle, aircraft, etc. Next slide. The classification of the radomes may be depending upon its shape, application, and materials, and also the plan of the talk is in this way. EM design of the radome and also radome fabrication. I will take a case study of a typical radome, which is used by indigenously of our group, RCI DRDO. Then how the radome is designed, then how it is fabricated and machined and joined with the next section and applied certain paints on that, and how it is evaluated and qualification of the radomes. And also I will throw some light on frequency selective surfaces and futuristic radomes which are in this which are under development. Next, sir. Generally, the effects of a radome on antenna. I hope everybody, you can interrupt me anytime for a clarification, please, sir. It reduces the antenna. Antenna is a device which transmits the signal and receives, which transmit impinges onto the target and get the return from the target and find out its characteristics of the target. So this is it is a eye or eye of any radar which sees actually what is coming inside, what is going outside of its view. So the radome which protects this antenna, it reduces the gain. Actually, more the gain, more will be the range we can see the target. So if radome is a protective device, because especially on air environment or space or vacuum or in any other different environment conditions, one should protect the antenna. That is nothing but a radome which protects it. In doing so, sometimes it reduces the antenna gain. If you see in the figure, for example, the antenna gain is around 10 dB. The reduces the gain by maybe 1 or 2 dB. A good radome says it is a reduction less than 1 dB. And sometimes it increases the beam width of the antenna. Narrow the beam of an antenna requires to specifically differentiate from the known target to unknown target, and also increase the side lobe level. Side lobe level is nothing but the unwanted signal which is coming into the through side lobes will definitely reduces the range of the antenna. And also the monopulse. Monopulse is a system in which one single pulse will send to the target and get the complete information of the target in terms of size, shape, and as well as where it is location. These are some of the technical effects of the radome. Important effect of the radome is, as it is a dielectric material, whenever there is electromagnetic wave travels from one denser or rarer medium to other medium, refraction takes place. Due to that, the target which is at a certain position X, it looks at certain other position. This difference between the target location is known as Borset error. The rate of change of the Borset error is also sometimes known as Borset error slope. This is very, very important for especially for airborne vehicles like missiles and aircrafts. Why? Because when the missile is delivered onto the target, if the target is moving away from the missile or coming towards the missile from a distance, if the dielectric material, because of that, it sees at some other location instead of a location X. This is known as Borset error. As Borset error minimum as possible is required for exact capture of the target. Next slide, sir. Typical radome, there are different electromagnetic spectrums, sir, right from the micros and RF. We start with the L band to L, S, C, X, KU, KA, W band. I have taken a typical radome specification of KU band. The length to diameter of this radome is 2.7. And shape of the radome, I have taken a ogive. I will explain you all that in detail. And fabrication, Borset error. These are typical radome, airborne radome specifications for internationally known specifications. Coming to next slide, sir. I will start with the design and development of slip-cast fused silica radome, which is a case study. In that, I will explain each and every what is radome and how it is, what is the different functions of it, how it fabricated, and how it is tested and evaluated. Next slide. Next slide, please. So radome development major, it is a multidisciplinary technology. Here it consists of first of all whatever major technologies involved in, that is fabrication, materials, engineering, computational, and joining and evaluation. Many fields, science, physics, chemistry, engineering, mechanical, electronics, and computer science. All these fields are involved in this. We will start with the radome design and analysis, and later the system how the system requirements are there, how it is fabricated. Once it is fabricated machine, how it is joined with the next section, And to protect the radome, some protective paints we use. Then how to evaluate the performance of the radome. Then how the radome is qualified for the to attach to the next section. This is all I will cover in detail. Next, sir. Next. Depending upon the radome shape, as I mentioned earlier, radome is a protective device for radar or antenna. It depends upon the different shapes, like where the application is there. For example, a ground-based radar system, it has to protect from the high winds and sun and dust. So it is hemispherical dome is sufficient for that. Whereas any other shape also we can use, but the best shape is hemispherical, where the bore set error and losses are minimum. Coming to the airborne system, it can be either ship launched, air launched, or ground launched airborne system. There is a depending in order to reduce the drag, we have different shapes of the radome. That is cone shape, ogive shape, one common shape, 3x4 series. In that all that ogive shape is a famous one. These are some of the ground station ground based radar. One of the powerful radar which we are at Kolar and Bangalore, which can detect around 650 kilometers away any target is coming. Next, sir. Some of the airborne radars from the aircraft, which we already know, very Typhoons or AIMS, advanced medium combat aircraft, which India is developing, or some of the Rafale systems which are we purchased from France. All those comes into the airborne systems. Their front section is nothing but a radome, which protects the electronics, all electrons inside the radome, and at the same time it will give minimum degradation of the performance. Next, sir. Some of the submarine launched radomes are also there, where once the radome is coming out of the system is coming out of the water, then it should have it should performance well with environment, water coming inside of the around that. These are some of the submarine ship based radomes, where we generally used e-glass epoxy or fiber type of radomes, which shows least performance degradation. Next, sir. Actually, what is the requirement of a radome? A radome is a lightweight. It should be a lightweight. It should have adequate strength and toughness to withstand aerodynamic forces during the flight. And it should have a good thermal shock. Thermal shock in the sense, when, for example, a missile is fired, its total flight time is around 20 seconds, let us assume. Within that, it reaches from a room temperature, a normal ambient temperature, to a temperature of 1000 degrees in 10 to 20 seconds. So there is a great thermal shock. The material should withstand that thermal shock. We have to make a radome with that thermal shock resistant material, so that high temperature and aerothermic loads it can able to withstand. And also the main purpose of the radome is to protect. At the same time, it should not interfere with the electromagnetic waves which it should propagate. So it should have a low dielectric constant, as low similar to as air. Air is a dielectric constant which is having a relative dielectric constant of 1. So any material which is higher than that, it should be very nearer to that, is a good material to the candidate material of a radome. And also it should withstand high resistance to dust, particle erosion, and rain erosion, especially when it is mounted on certain aircraft. It continuously undergoes different sorties, so before actually finally launched. So it should withstand all that particle erosion and rain erosion and resistant to the dust. And also it should have a good joining characteristics with the next metallic body, and also it can be easily machinable to the required shape. It can be easily should be made into the required shape. If it is not required, shape is not maintained, then performance of the radome is not ensured. So these are main requirements of any radome requirement. Once if it is on board, the requirements are also very stringent, because it should be lightweight. It should have it should withstand thermal shocks and loads that are coming onto that. At the same time, it should be transparent. It should have missionability and joining capability with the next sections. Next slides. So based upon this material, the radomes are divided into basically ceramic and composites. and some of them are sandwich type multi-layer and a combination of the above. In first of all, depending on the temperature, if it is a very high temperature, more than 400 degrees centigrade, all composites, whatever we use fiber or sandwich or fusil, they will become very weak and they will melt also. So only solution for the high temperature radons more than 400 degrees centigrade is ceramics. And under the 400 degrees centigrade, we can use composites. And for being a radon is a narrow band, like it's a band pass filter. To increase the bandwidth, we go for a sandwiched multi-layer radon. Sometimes we use hybrid type of radons where we require the shape of the hybrid comes from the shape of the radon. We use spherical, hemispherical, and elliptical, ogive, and power series type of radons. Some of the key candidates today, these are for ceramic radons, which will have a high temperature. For composites, generally we go for E-glass epoxy, E-glass polyamide, quartz cyanide ester, quartz polyamide, and such materials which can withstand up to E-glass epoxy can go up to 100 degrees, 150 degrees centigrade, whereas quartz cyanide ester will go up to 250 degrees centigrade, whereas E-glass polyamide will go up to 400 degrees centigrade. Coming to the ceramic materials, there are a lot of ceramic materials are available like aluminum oxide, fused silica, magnesium aluminate, aluminum sulfate, silicon nitride, boron nitride, magnesium oxide, beryllium oxide, and Cylon, magnesium sulfide, silica composites. Under that, fused silica is a favorite material for especially for missile applications because of its abundant nature, availability, and low loss and low dielectric constant with high thermal shock. The thermal shock means, as I told, within seconds it can reach from room temperature 30 degrees to 1000 degrees centigrade. It can withstand. Any other material in this series, they will not withstand such high thermal shocks. That is one of the advantage of fused silica. Next to that, generally we make onboard radomes with silicon nitride, which can go even further high temperature, like up to 1400 degrees centigrade. If you want even further higher like hypersonic missile, hypersonic vehicles, there we use boron nitride in a combination of silicon nitride and fused silica. Especially they are important for re-entry environments. Next slide. Coming to EM design of the radom, we just get the inputs from the system requirements where we should use what is the purpose of the radom and what is the specifications of the radom. That all includes the operating frequency, the shape, and material characteristics and wall construction. For example, operating frequency means if the operating frequency is say S and L band, then the thickness of the radom is very, very large, 20 to 30 mm. So we can use even a thin wall radoms. Depending on the frequency, generally the radom thickness of the radom is a lambda by 2 thickness or a multiple of that one. And shape, if it is a ground shaped or we use hemispherical. If it is onboard also subsonic, let us assume less than the velocity of the sound, then we use ellipsoidal or spherical radoms. And if it is a supersonic and hypersonic, then we have to go with the shape of ogive and tangent ogive, hybrid shapes, and power series. Coming to classification of the radom, depending on the wall construction, thin wall radoms we can use. If the requirement is the loads are very low, then thin wall radom can be used. Half wavelength radom we will use, and it's multiple. If the as you increase in the frequency, the lambda by 2 thickness itself is also very small. So in that case, we can go for multiple lambda thickness. For example, at W band 100 gigahertz, the thickness of the radom is around 2 mm. So 2 mm radom is very difficult to withstand all the loads and temperature that are coming onto that. So we'll go with a multiple of lambda, maybe 4 mm or 6 mm thickness. And also for onboard seekers, they are narrow beam antennas, narrow bandwidths. sometimes, especially to cater for the wide bandwidth antennas, bandwidth radomes we use. For that, we go for a sandwich radomes. A sandwich, B sandwich, and C sandwich, and multi-layer sandwich. Sandwich in the sense, here the skin layer of the radome is high dielectric constant, and core layer of the radome is low dielectric constant. And again, one A sandwich means two skin layers and three skin layers and two core layers, such that like that it will go. It increases the bandwidth or where which band we are, which lower side band we are looking at, or higher side band we are looking at. Based upon that, the thickness of the radome is chosen and shape of the radome, and also wall construction is chosen. Next slides. You can interrupt me, sir, whenever you feel I need some more explanation. I should give some more explanation. Coming to radome analysis, there are different electromagnetic techniques to analyze the radome. Simple and easy optical, geometrical optics thing, and also physical optics approach, which we generally do with the ray tracing method. And more complex methods are method of moments, plane wave spectra, and some of the numerical methods like FDTD, FEM. These techniques are also used with the computational power to find out the complex radome analysis. Next slides. Continuing the numerical methods, there are different electromagnetic solvers are available now, like FICO, Ampere, Newfasant, CST Micro Studio, HFSS, some of the few 3D electromagnetic software tools. There we have to define our radome structure and import in, we model the radome in SolidWorks or ProE, then give as an input and define an antenna pattern, then it will give the analysis of the radome. Some of the, for example, if you take a FICO software, it is a full simulation software frequency domain. It is having a lot of sub routines like method of moments, asymptotic solutions like PO, large element physical optics, ray tracing, UTD, such methods. In time domain, FDTD method is also available. Next, sir. For this, to analyze a radome, first we design how to design a radome. First of all, we will take an antenna array pattern. If your antenna radome goes into hand in hand pair, as a pair they will go. For example, a single element patch we design for a frequency, then we will expand it to a planar array of monopulse antenna, where we will get sum and difference patterns. In the as I shown in the picture, the top one shows, middle one shows the sum pattern of the antenna, and the bottom middle one shows the difference pattern of antenna. Where by using these patterns simultaneously, we will get the complete information of the target about its range and also its location. Next, sir. This is a 3D simulated pattern of radome radiation pattern in E-plane. Next, sir. Sir, in order to some of these are simple things, whatever I told earlier. Now coming to the very hyper for a complicated things like number of layers or more, and we have to have a bandwidth. In the figure shows here is at least A sandwich radome with 3 skin layers and 2 core layers with some paint other in between. These type of layers, these type of complicated radome requires a huge computational time and huge computational requirement, such as high performance computers we use. One of the typical radome which solve the radiation pattern with sum and difference, with radome, without radome, with antenna and sum and difference, with radome sum and difference are plotted in the figure left top left side, and the solver used FDTD. And mesh size here 1.5 crores of shells we used, and it take a huge computational time of 100 nodes with a capacity of 3 terabytes with a cluster performance under teraflops. This type of radome takes with a memory of 600 gigahertz GB, with the nodes of 70 nodes and resulted in 12 hours to give you one particular bore set error angle. Next, sir. This is a complexity of a radom simulation. This is one of our high performance computer system which is installed in DRDO Hyderabad, which is one of its kind. Now it is in a petaflop facility is available. It's a national facility. Any organization on request basis can utilize the facility. It's just coming up at RCA campus. Next, sir. This is the typical radom dimensions, whatever for airborne missile applications, where the radom ceramic radom shell on the right part, the red side red shows inside the radom, which is a invar ring. This purpose of the invar ring is also very critical because these radoms will go on a high thermal shocks. Like the temperature of the radom goes from 30 degrees to 1000 degrees in less than 10 to 15 seconds. So the next, the coefficient of thermal expansion of these ceramic materials are very, very small. The next section, which is a metal, whose coefficient of thermal expansion is very, very high, at least 1 order or 2 orders more. So there is an uneven CTE difference that leads to the crack of the radom. So in order to reduce that, invar material is developed. This invar is 30% of nickel and rest of the things are iron. And depending upon this combination, it is also having a low CTE, thermal coefficient of expansion, to nearer to the ceramic radom. Because of that, this is a candidate material to join the radom. Radom can be joined in subsequent slides. I will show. This is a typical radom dimensions. Generally, L by D ratio is around 2.7. From that, we can calculate any type of the radom. Next, for example, if the dimension length of the radom is 500 mm, the diameter may be around 180, 200 mm. This is a 3D model generated through physical optics, analyzing radom effects on seeker antennas. Next, sir. This is one of the typical radiation pattern of the antenna and radom. Antenna alone, and when the radom is placed, this is a very important, means very optimized radom performance what we got indigenously. Till now, next slides. This is a transmission loss of the due to the radom. You can see the radom is showing maximum transmission loss of around 0.6 dB at the bore site, and it is coming down to sometimes it is coming down to 0.4, 0.3. And as we are going at the larger scan angles, where we can see the flat radom surface, because of that transmission loss is minimum, and also bore set errors. Next slide. These are the bore set errors in minutes, whatever with respect to a scan angle. 1 degree is equal to 60 minutes. So we can see it is 1/4 of a degree variation. It is at least especially coming at the cone angle of 10 degrees from the center of the radom. Next, sir. These characteristics we have to minimize. The bore set error characteristics should be minimized. Next, sir. Next, coming to the once the EM design of the radom is completed, we have to see the effects, environment effects onto the radom. They are coming as aerodynamics, which proper aerodynamic shape to minimize the aerodynamic drag. So because the missile or any aircraft which should have a minimum drag to move longer ranges, to get more, to use more fuel, means for the longer ranges, the same fuel for longer ranges. So aerodynamic shape becomes very, very important. If the shape is not perfect, the high temperature comes onto the system. So with the shape, because of the drag, frictional drag, we have to design a shape in such a way that this aerodynamic drag is minimum. At the same time, we should not interfere the electromagnetic performance of the electronics which are below the radom. So it depends directly on the material science, which are different type of materials, their combination which satisfy the requirements is used. This is a huge science. We are still working, evolve the new materials to optimize the performance of the radome. Once the aerodynamics are okay, then it should have also the thermal temperatures coming onto the radome also important. These temperatures, some of the materials, the electromagnetic characteristics changes with the increase of the temperature. So we have to choose in such a way the material which is fairly constant over the long range of flight, the dielectric constant loss tangents, and also if that there is a change, we have to compensate those losses with characterize them properly and compensate them. This is what required for electromagnetic design also. Next. Next, sir. Once the material is chosen, whether it is acceptable for electromagnetic performance or not, we will see. That material dielectric constant, we have different methods used to find out its dielectric constant. One is a probe method. Second one is a cavity resonator and free space method. Next, sir. Next, please. This is a network analyzer. The right side is of network analyzer, where the computer, some software is there with HPAB cable, where the probe, the sample, which is an orange color, we placed onto the platform, where we can find out the slope by using S parameters. From the S parameters, we find out the dielectric constant of the material roughly, approximately. Next. This is the actual setup which is at our RCI, where we can, the white one, these are different samples which are placed on the cloth. These samples are measured using dielectric probe. Next, sir. The dielectric constant of this one, for example, Teflon, it comes around 2.1, 2.2 here, and with a loss tangent of 0.0004. Next. Next one is a waveguide measurement setup, which is more accurate compared to that. Whenever the sample whose dielectric constant is unknown, then we use the Ellier method. Then if the dielectric constant approximately known, then we'll make a waveguide sample. According to that, then we use a network analyzer, 2-port network analyzer, and we find out the by using a waveguide adapters and place in a waveguide flange. We find out the S parameters. From that, we derive the dielectric. Yeah, ఇప్పుడు connect అయింది. Am I audible, sir? Now, can you able to see me?
Yes, sir. Now we could able to hear you, sir.
Yeah. There's a computer adapter, there was some problem. Now, coming to the waveguide setup, measurement setup, here what we do is, next slide, please. We'll show clearly. Next slide. You see, you can see the waveguide setup. Here we'll make the samples where we'll put the dielectric sample and put into the waveguide setup, and we'll find out the dielectric constant values. Next slide. So you can see here the dielectric value is more accurate. It is coming around 2.01, something like that, and last tangent is also very, very accurate. Next slide, sir. So these are based upon we sometimes we want the last tangent value also. Dielectric constant is having a real and imaginary part. That imaginary part is a last value which contributes the dielectric loss in terms of heat, which is undesirable. So we will try to have a low dielectric loss material. to accurately measure the low dielectric loss, what we do, we developed a cavity method, because this cavities, next slide please. These cavities works on resonant phenomena, where we can get more accurate of loss tangent values. The table shows the dielectric constant and loss tangent values by using for different materials like Teflon, RT-Duroid, and Cylon materials, where at 9 gigahertz to 9 to 10 gigahertz, where we can see the literature value and loss tangent value are closely matching. Next slides. These are different types of cavities that what we developed at our place. These are very important to characterize the dielectric constant. Next. And loss tangent. Next, sir. This is a summary of all these different methods: waveguide method, probe method, and resonant cavity method. Sometimes these methods are room temperature methods. If you are not having an access of the material, then we go for a free space measurement material, and also the temperature, how the dielectric constant loss tangent varies with the temperature, that we will see with the free space measurement setup. Next, sir. These are some of the components we characterize at our place at X and Ku band, dielectric constant values of fused silica. Next. And this is there are two resonant methods that are popularly used: split post resonant method and split cylinder resonant method. In split post method, we will put that sample into the gap between the two dielectric coupling loops are there. From that we will get the S parameters. From that we will find out when the resonant cavity frequency, when the sample is not there, the cavity resonates at one frequency. When the sample is put, the resonant cavity shifts the frequency of resonance. The difference in the frequency of resonance indirectly calculates for us what is the loss tangent value of the radon material. Next, sir. This is high temperature, high free space dielectric measurement setup, where in between the sample is placed. Sometimes we put a hot chamber in that place, so that we calculate the dielectric constant with the temperature also. These are some of the dielectric measurement methods. Next. Next, sir. These are some of the samples what we measured. Once the radom material is characterized completely, then it is going for a next slide, fabrication. Hello, next slide, please. The fabrication of the radom, it is a different type of radom. I'm mainly kind of covering the ceramic radom because of time shortage. Fused silica radom, which is a popular radom which is used for all our missile programs, where we take a fused silica powder. This is nothing but naturally available fused silica in India, Rajasthan, and Chennai, and in Hyderabad, near Hyderabad also we will get the silica. Silica nothing but a earth excavation material, which is purified to 99.99%, then crystallined and fused to a temperature of 1700 degrees centigrade. Then they will then it is make it a powder that comes as a fused silica powder. That fused silica powder is mixed with pure water or mineral water to make it a slurry, which is known as slip. That slurry is put into the plaster of Paris mold. This is one of the technique we use. There are different types of techniques to make the radom. One is slip casting, gel casting, so cold isostatic press, like that. In that sintered radom is casted, then it is put into the dry oven, then a very big furnace to sinter the radom to high temperatures of 1500 degrees centigrade, so that the radom becomes sintered radom. Once the radom is there, then it is machined with diamond cutting tools to become a finally usable radom of a given thickness. Next, sir. This is the same procedure, whatever I explained in that. First, the silicon powder is with gel cast silicon nitrate radom, mixed with dispersant, then slip prepared, then plaster Paris mode they will put, and then sintered to get the silicon nitrate sintered radom. Next, sir. After fabrication, the casting modes of the radoms are shown like this. These are the two different type of fabrication like SIP casting and gel casting, what I explained earlier. Next, sir. Once the radome is fabricated, it should be it should be machined to a required shape. Next slide, please. This is how the radome is made. This male and female radome. In that we'll pour the material so that the radome comes like this once it is open. Next slide. Once the radome is sintered, it should be because of the especially this sintering process is a natural process. So the radome thickness is not uniform throughout that. There is a lot of ovality and also there are some blowholes. In order to remove them, we should machine it to the required profile. That required profile is one of the critical step of a radome development, where it is machined with a diamond tools and by using a lathe or diamond grinding tools we use to machine the radome inside and outside radome. We can see to hold the radome is a brittle material. To hold that is a non-metallic adapter we use, and also telescopic machining tool we use to go especially inside of the radome to cut. Next slide. This is outside the radome is much easier compared to the inside machining. Next slide. Where the tip of the radome will be held by a rubber spindle, and the radome is machined outside. Once inside of the radome is machined, next outside of the it is vice versa. We can use some people, they can go for a outside machining. If the inside machining is more or less near net shape, then we'll machine only at outside. Otherwise, you have to machine it both the sides. Next sides. This is fabricated machined radomes of two different materials. One is slip cast fused silica radomes. Second one is reaction bonded silicon nitride. The left side shows goes up to 1000 degrees centigrade, whereas right side goes up to 14 to 1500 degrees centigrade. Next slide, please. Now, once the fabrication radome is available, it should join with the next joining with the mechanism bulkhead. This bulkhead, as I mentioned earlier, it is made up of Invar material. Next. You can see the radome is added to the next section by using glues and threads, sometimes active brazing, and by using some glasses, different type of glasses, fusing between the radome and antenna. This is how the radome is joined to the next bulkhead. Next. These are some of the glues that are used to join the radome. The old technique is of threading the ceramic radome and join with the bulkhead. But now, because of the threads, the ceramic radome weakens, so we are not using. We will push fit type of radome with the help of a glue. Now we are using. Next slide. These are some of the advanced technique with the help of DMRL we are using, where the temperature is very high. Then we cannot use glue and other means because they will melt. So in order to tackle the high temperature, especially at the bottom temperature 950 to 1200 degrees centigrade, we use basing alloys like TecoSil and copper and silicon or TecoSil material as a joining material, so that the ceramic will be joined to the Invar bulkhead. This will give high strength and also it can withstand very high temperatures. Next. Once the joining of the radomes is also over, because especially these radomes next, some of the paints, thermal and moisture paints we have to use. Fused silica, some of the materials which are hygroscopic material, they will absorb the water droplets. The disadvantage of water or droplets is dielectric constant of water is very high, 80, whereas the material that what we are using is around 3 to 3.5. So, in order to protect from water, we use some protective paints, especially on outside and in moisture from inside of the radome, so that these paints will protect from moisture as well as high temperature environment. The importance of these paints are they should be carbon free or chart free, so that they should not interrupt the electromagnetic performance of the antenna which is put inside of the radome. Next, sir. Next, these are some of the paints available, commercially available. Next. Next, sir. Once a radome is made, that should be evaluated for electromagnetic performance. This generally we use a different type of ranges, compact antenna test range, where these antenna radomes are qualified electromagnetically. There to find out the radome performance with respect to different scan angles, we have to make a special arrangement that such that the relative motion between the antenna and radome should be available. That is mounted on a gimbal mechanism. This total radome along with the antenna is measured in a compact antenna test range, where this range is used. The parabolic reflector, what is shown, reflects the rays parallel to the antenna's surface, so that we can characterize the antenna in free environment. Next. This is another compact antenna test range at RCA Hyderabad, which was installed at Dr. Kalam's times. Still, it is operational. Next. Sir, these are some of the sintering furnace I put, which used for the radome fabrication. If some moisture is there, then we'll put into the furnace and reduce the moisture, then we'll paint the radomes. Next. This is a radiation pattern obtained with and without radome antenna pattern. We can see at the bore side, the loss is around 0.8 mm, 0.8 dB. This shows the excellent performance of the radome, excellent good design of the radome. The next. We can see the performance insertion loss of the radome over the frequency band. At center frequency, it 0.9. It is a narrow beam radome because it works here only, the requirement is around 100 megahertz. So we work around 100 megahertz only. Once that is why these radomes are known as monolithic radomes or single narrow band radomes. Next. Once the radome is made, it has to be qualified for its performance in terms of different qualification parameters. Like next. These are some of the tests like static tests, sand and dust, humidity, thermostructural, rain erosion, blown rain, vibration, high temperature, X-ray, whether any blowholes are there, cracks are there, acceleration, low temperature, high temperature, shock, CMM, EM characterization. These are the tests generally used for any radome to be qualified. Once the radome passes all these tests, then only it is known as a qualified for the product to be used. Next. These are, that is what in brief a case study of a ceramic radome which is used for airborne vehicle. Now the advancement of the radomes, latest advancement of the radomes frequency selective surface. As I mentioned earlier, all our airborne vehicles, when the enemy radar impinges onto the airborne vehicle, it gets reflected and it is detected by the enemy radar. So what the requirement is low radar cross section. That low radar cross section we achieve with the help of radome shape and also radome design also. That is where the frequency selective surface radome comes into picture. The frequency selective surface radome is nothing but a band stop or band pass filter which is used on board. Next. Why we need radome, FSS radome to reduce the RCS and also minimize the reflections in in-band frequencies and deflect and other band.
40 minutes now.
Pardon, in the 5 minutes I'll take. Next slide, please. So these are the different methods of mechanism frequency selectivity is used. It can be absorber, it can be absorber frequency selective or radiated frequency selective surfaces. Next, please. How to design such a frequency selective surface onto a radome is a very, very complex thing. First, we go with a unit cell, then extend it to array design, then finally onto the radome. That is how we go in step. This is a state-of-art technology. Very few countries in the world can use this frequency selective surface of radomes, especially for fighter aircrafts like Typhoon, our AMCA, AMCA, and also Rafale systems use this type of design. Next. These are some of the elements used for the type of this frequency selective surface radomes. Typically, I will show next slide, please. I will show typical two types of FSS, as I mentioned earlier, band pass and band stop. Band stop is a way where we don't want our detection. There we put the band stop structure. The band pass FSS, where we want our transmission of the antenna, there we will put such type of frequency selective surface. Next. Some of the material for this is advanced composites, specialized polymers, and silicon carbide and other lightweight durable materials, which can embedded into the actual metal conductive layer so that it can act as a frequency selective surface and filter. Next, sir. These are some of the designed frequency selective surface radome, like one layer, 3 layer, and 5 layer. As we increase the number of layers, the steepness of the curve increases, and also we will have a exact rejection of the signal which is required. Next. Some of the futuristic radomes in this field: high temperature, high supersonic, hypersonic missiles, where the temperatures are ranges from 1000 and beyond that, and also high electromagnetic pulse. These are very new development where we send high power electromagnetic pulse so that all our electrons will be disabled. So in order to protect that device or to launch that, we require a radome which can withstand high electromagnetic energy and also strength. After that, some of them are conformal antenna, conformal radomes, which integral part of radome and antenna, which can take the shape of a radome and confined to the required airborne vehicles. Some of the suitable materials are silicon nitride, boron nitride, alumina. Next, sir. Some of the futuristic things what we are where we are today, and we are with silicon nitride radomes. In futuristic silicon composites, we will go with a broadband hybrid ceramic radomes, which can be used for space applications also. Next. This is another roadmap what we are doing, whatever I explained earlier. So we are radome with a shorter array antenna, wideband FSS radome where we are now, and we go for embedded radomes in the near future, maybe 2030 by 2030. I think I am coming to the end of the presentation. Next slide. Thank you, sir. Thank you for your valuable patience, and this is a new topic. I guess you can ask me any questions, any clarifications you require.
Sir, thank you very much, sir. It's a wonderful topic, sir. With a very short notice, you could able to come and speak on the very important, very auspicious day for engineers, sir. Science Day. This is the National Science Day event, sir. So we have gone through all the radome development and all the major technology involved in it. We went to a micro level and very highly descriptive, sir. And one more thing, we should also very thankful, sir, for you who want to become the member of Institute of Engineers. I think we can carry forward with your FIE membership in future with IEI and to next level, sir. And I think probably to address the students, we'll be having often get into this 1 day and 2 day events. We would appreciate if you could also participate and share your expertise to the student fraternity, sir. In future, we would like to involve you with more of IE, sir. And I think probably it's already 7:30, sir. Any questions? I think probably would be appreciate if you could answer offline, sir. Or we'll go with 1 or 2 questions, sir.
I have a question.
Okay.
Sir Ramu Garu.
Yes, sir.
Sir, it was a really fantastic, I can say, presentation, and the content also so good. No doubt in that. I have small 2 questions. One is what considerations you need to take into account when a radome is designed, especially when it is integrated with the 5G technology.
5G technology is because the main concern is low loss, sir, because we use very in reception and transmission. In reception, the signal strength should be in general, it is very low. So we should use a very low loss materials like artiduride and some of the material which dielectric constant nearer to air. And also it should withstand hygroscopic, non-hygroscopic, like it should not wet the radome surface and chemicals. These are the two important things it should consider before making a radome. Because temperature is not a requirement there, because the normal temperature of our 5G requirements is around 70 to 80 degrees centigrade. Most of the materials which are coming up with low loss are adequate.
Thank you, sir. Moreover, the 5G operates on three different bands, low, mid, and high frequency. So
Yes.
what is its impact, or how it interacts radome technology when it is used at millimeter frequencies?
Sir, if you are using at millimeter frequency, the wavelength becomes very, very narrow, means very, very small, maybe around
Yeah.
1.5 to 2 mm. So, very small change in the fabrication machining tolerances will directly impact. So, we will, in that, what generally we do is we will try to shape the radome hemispherical sort of thing so that loss will be minimized. And also, we will try to maintain the accuracy of the radome shape.
But one thing, sir, because this nothing is a small technology comes into picture because of this millimeter frequency. And
Yes.
is that a small technology in the small cell? What it is, we use it as a base station. Does it has a radome and what type of material is required? Because it's very less voltage is given for a small cell. That's the main advantage of even 5G technology, energy saving of 99%, 99.9% energy saving consumption is also comes into consideration. Do you feel what type of material is can be used there in, because as of now, though they are saying in India we are not using millimeter frequency, still we are at a sub-6 only. So
Yes.
in future, definitely the millimeter wave frequency is going to be used. Though the Geo has purchased 26.5 gigahertz, but actually they are not operating at that frequency. That its performance is only 16 point something times faster than the 4G.
Yeah.
So you suggest any other material than this fiber, whatever it is being used, optic now used for the present situation? Any
Sir,
combination of materials?
yeah. It is a definite Teflon or silicon based
Oh.
materials which can, and also graphene. Graphene is a new material developed. It is a very thin layer of sub-micron thickness that will give you a highest performance. That in Nalgonda in Telangana, there's a lot of reserves are there of graphene. That is one of the candidate material. Apart from that, in general, Teflon and silica-based materials are low-loss materials. Based upon that, they can fabricate. Right now, very shortly, maybe within a few years, we are going to have a terahertz and 100 gigahertz transmission communication also is going to come, where we will get a huge bandwidth and we can use IoT in Internet of Things many folds. All technologies coming up very shortly. Within a couple of years, we can see a sea changes. Geo being a advanced using company, it is going to be the first company I feel that they are going to implement such things.
Very good, sir. Thank you very much.
Sir, nice of you, sir. It's a wonderful lecture, sir. As Brahmareddy Garu also said.
Yeah,
So
sir, I want to interrupt you. Just I apologize because today when VIP visit was there at our place, because of that I could only came for the webinar at 6:30. I apologize for that, and I'm grateful that if you I'm part of your further lectures and other things. It is an honor to me. Just I want to confess this.
thank you so much, sir. It's not the question of time, sir, but still your presence made a great value to all the fellows, fellow of Institute of Engineers and the research scholars, and also lot of participants. The August gathering of today's webinar, sir. We also acknowledge the presence of Ravi Kumar Garu, Brahmareddy Garu, our past chairman, and G. Kondalrao Garu, Kishore Garu, Narmada Garu, P. Srinivas Rao Garu, Prasad Babu Garu, Vijay Prasad Garu, B. S. Rao Garu, Shiva Garu, and past committee member Subbireddy Garu. Sir, with this, sir, thank you so much, sir. I think we would again come back to you, sir. Time is not a matter, sir. Definitely, your expertise really has gone into percolated to most of the members who are part of this webinar, sir. And we thank your presence here, sir, as the keynote speaker, sir. And we also thank the chairman of Institute of Engineering, G. Venkat Subbaiah Garu, and the committee member and the convener of the event, Mohammad Mohiuddin Garu, for making this event a grand success, sir. We also acknowledge the presence of the immediate past chairman Brahmareddy Garu, and immediate past chairman and the present council member Ayesan Raj Garu for their presence here, and all other members who are participating, sir. And it's a wonderful topic, sir, radome technology. With this, I think we come to the end of the National Science Day event, sir. Before we move out of this, we would appreciate all to stand for the national anthem, sir. Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।